Colloquium. So today's speaker is Magnus Svard from University of Bergen, Norway. And he's an expert on numerical methods for fluid flow equations. And today he's going to talk about convergent finite volume schemes for a different compressible Navier-Stokes model. So over to you, Magnus.
Thank you. Well, so this is my pet project that I've been working on for quite some years now. And yeah, there it is. Okay, so I want to begin with a bit of a background before I get to the maths that you are probably more interested in. So I've been working on compressible flows basically for my entire career, and what I would like to develop at some point is more or less a CFD code that is predictive in the sense that we know that it gives the right answer, although we don't know the answer. So what I mean by that is that anyone who does CFD knows that by tweaking and tuning and so on, you can get the right answer if you know what you aim for. And I want to see something that is predictive that you can, in basically the same way that you can do in other areas like structural mechanics and so on, where I think models and numerical solutions are much more reliable. So what we need for this is basically an accurate model that is a set of equations, and we need to know how to solve it, and that it is solvable. And anyone who has been working with the Navier-Stokes equations knows that that is still unknown. We don't know if it is well posed and solvable, basically. And this is something that most of us accept, that this is a problem that will be solved at some point. But I've been wondering why it is that it is so difficult to solve or demonstrate that there are solutions to the Navier-Stokes equations. So I went back and looked at the derivation and so on, and it turns out that there are a number of modeling choices that you do in the Navier-Stokes equations that causes all these problems. And so the compressible Navier-Stokes model, that's basically, you have an ideal gas. You assume that the gas is ideal, rather, and which means that it behaves as billiard balls bouncing around in space, and there is no interparticle forces, and so on. And another assumption that you make for the Navier-Stokes equations is that locally you have thermodynamic equilibrium. That means that at every instant you can view point values as being somehow in equilibrium. That means that any gradients on small scales will quickly diffuse and even out differences. And it's derived, the Navier-Stokes model, by looking at the Lagrangian mass element, and then you view that the motion of that mass element in the flow, and you set up equations by looking at stress force and so on. And the energy equation is sort of an add-on where you also then add in heat conduction. And here the way I use conduction is that it's a diffusive process in some sense, but it's going on by collisions rather than movements of the particles. So it's by colliding into each other that heat is transferred on the atomic level. So this is sort of the backdrop for the Navier-Stokes equation. And what this means is that there are a number of properties you get when you derive the model in this way. So one thing is that it's very, very difficult to prove that solutions somehow guarantee that density and temperature remains positive. Another thing that you can see is that at adiabatic walls, if the entropy gradient appears to be non-zero, so the entropy is well defined, and you can just compute the gradient, and it's clearly not zero by the boundary conditions that you have. And also, if you look at if you make a CFD run, you typically need some far field boundary conditions that truncate the domain, and that's very well defined for the Euler equations, where you typically use some kind of characteristic boundary conditions, and that you cannot make sense of for the Navier-Stokes equations. So the continuity equation basically messes things up. What's also interesting is if you look at a very, very small scale, the assumption that I talked about on the previous slide here, that you have local thermodynamic equilibrium, that should mean that on small levels, small length scales, diffusion should govern everything. But if you induce a very, very small thermodynamic perturbation, you will always induce a macroscopic velocity. There is no way the system can relax without it. And if you move on and look at, for instance, multi-component flows, then you would expect that the diffusion between different components is governed by Fick's law, which is well established, and that cannot be used. And you have to jump through a number of hoops and loops in order to get a model that satisfies the continuity equation for the combined density. And also, if you look at the stress tensor and try to interpret that when you go back to the Eulerian frame, which is where you typically do CFD simulations, you see that it's quite unclear what these terms actually mean and how they affect, how they sort of make up forces in the right directions. And all of this is caused by the hyperbolic continuity equation, which in turn is a consequence of the Lagrangian modeling. Since you are looking at the motion of a mass element, it is by definition a hyperbolic continuity equation. And it is this that causes a number of mathematical and numerical problems. So I went back further to see what are the principles that you use and what principles should you use when you derive a model. So the first principle, I'd argue, is the conservation of mass, momentum, and energy. And another first principle is that at the sort of macro scale, it is diffusion that is the first principle. So molecules move randomly around, and they transport all their mass, momentum, and energy. This is the sort of the way a gas works at the atomic level. And then I write this, it's not a first principle, but we do, in CFD, we typically compute in Eulerian frames. So why not derive the model in an Eulerian frame? It is strange that you need to jump back and forth when you derive the Navier-Stokes equations. And I'd also argue that the Navier-Stokes equations are not derived from first principles, because viscosity and the stress tensors are actually derived properties from diffusion. And also you use Newton's second law, which is in principle also a derived property from Noether's theorem. And the other thing one should realize when looking at a gas is that molecules move around. They do not just bounce into each other. They exchange places. This is very different from a solid, where the atoms are basically in fixed places in relation to all other atoms. In a gas, they simply move around, and they pass each other by quite some distance. And this is the diffusion process. And if you then derive a model, and you remain in the Eulerian frame, and you see that atoms that bounce around diffuse all principal variables, then you get another type of model, which is what I call the Eulerian flow model. So on the left-hand side, we have the standard Euler equations that I assume that you're familiar with. And on the right-hand side, we do not have the Navier-Stokes terms. Here we have basically a simple second derivative diffusion. So here, nu here is my diffusion coefficient, and it acts on rho, v, and e. And then I have also added this term, which I will come back to. This is more or less for technical reasons, although you can give it some interpretation, but I don't think it's necessary from a physical point of view. And the nu here, in order, so you can look at this model, and if you set rho to be constant, and then you immediately see that this reduces to the incompressible Navier-Stokes equations if you set nu to be mu over rho. So mu is the dynamic viscosity that appears in the Navier-Stokes equations. In this talk here, in this work that I present here, I take nu to be this main coefficient here, which is what I think is the physically correct one, but I also need like a technical assumption that it has some linear dependence of rho as well. And this term here is sort of like a radiation diffusion term. It's also like a technical assumption. So the kappa r here has to be very, very, very small. So it basically does not affect anything. So it is this term here. And that is the main diffusion coefficient. And I should also say the reason why it is the same coefficient here is exactly what I wrote here, that a molecule that moves around will move. It has a mass, it has a momentum, and it has an energy. So all of them will be diffused at the same rate, because the diffusion coefficient is basically the rate at which the molecules move around.
So Magnus, I have a question. Sorry.
Yeah, go ahead.
So this nu, it does not depend on velocity, right?
No, it can't depend on velocity. No.
So
If
this
it did,
because
then
of,
it wouldn't.
I mean, this Galilean invariance you need to preserve, right? That's the reason, or?
Yes. No. If it has to be Galilean invariant, of course. So
yeah.
it cannot depend on the velocity. That's correct.
Okay, and do you have any isentropic version of this, just like Navier-Stokes Fourier?
Come again.
I mean, it's like isentropic version of this compressible model. Do you have anything?
Yeah, you can derive that. That's just a matter of, well, it's basically the same thing. You set P equals rho to the gamma. Okay. And drop the energy equation. So it's basically the same, or very, very similar.
But diffusion could be density dependent, right?
What? Come again.
I mean, diffusion coefficient is density dependent.
It is, yes, it is.
Okay.
So yeah, so maybe I should say, so basically what you have here is a logarithmic diffusion. So it is a very, very weak mass diffusion in some sense. And here you get a logarithmic diffusion scale with V, and then you get more or less the same diffusive terms that you have in the incompressible equations with this mu over rho. So it has many, many similarities to the incompressible equations, you could say. All right, and here is just to show a little bit. So of course, the most remarkable thing that people usually don't like is that it has mass diffusion. And here you see what happens when you add mass diffusion. So here is a bit of an exaggerated picture. So I have exaggerated the oscillations that you see here, but these are not grid-sized oscillations. These are on a much greater scale. So the grid is much finer than these oscillations. And you see that the Navier-Stokes, if you do not add any artificial diffusion, you do get some oscillations in the density, while in my system you get a perfectly smooth flow. So this is just to illustrate that there are differences between these two systems. Right, so now I come to the mathematics. So what I will consider is a 3D box, and I have adiabatic walls all around. So that means that I have the no slip, the velocity is 0, and I have that the temperature gradient is 0. So these are the standard Navier-Stokes boundary conditions. And since I have a fully parabolic system now, I also need to add the rho dn is 0. And what I will briefly outline here is the procedure to demonstrate that there are weak solutions. So my goal here is not just to prove that there are weak solutions. I also want a numerical scheme to compute them. So I derive a priori estimates for the equations, and then I try to find a scheme, and I try to derive the same estimates, and then I must show that it's solvable in time, basically, because I have a semi-discrete scheme, and then I demonstrate convergence to weak solution as the grid size go to 0. And here I will stick to 1D in my derivations just to save space, but everything is derived in 3D in the paper. So a priori estimates. So as usual, you assume that you have a smooth and admissible solution when you derive them. And the first thing you derive is basically from conservation. So you take the continuity equation and just integrate it. If you now assume that rho is positive, then you get a bound on rho in L-inf and L1. And everywhere I use the boundary conditions. So these boundary conditions will make sure that all boundary terms just vanish in all these estimates. So this is the first estimate. Then I do the same thing for the energy equation, and I can then get a similar estimate for the energy. And the energy is a sum of pressure and kinetic energy. So I can split it up and get estimates on those two as well. So these you would be able to get for the Navier-Stokes equations as well. It's the same. Next, I turn to entropy. So I integrate the entropy balance. I derive the entropy equation and integrate it. And here, well, you need to use the previous estimates in order to demonstrate that this term remains bounded. So you need the previous estimates to control it. And then you get from the diffusive terms, you get the number of estimates on the gradients. So for instance here, since I assume that nu has a linear component, I get rho times rho here, times ln rho, which gives me this estimate, and so on. And the strong radiation diffusion gives me a good bound on temperature as well. And since I already have rho in L1, I can use the Poincaré inequality and this rho x inequality to get rho in H1. And from here, you can then move on and demonstrate that now density has to be bounded away from 0, at least on a subset of non-zero magnitude. Which is important later for other estimates. And then you can, so for instance, you can show then that you get that T is bounded on this subset, and then you can use Poincaré and the previous estimate to get that T is in L and T 3/2 is in H1 and so on. Then I move on to kinetic energy and again integrate that equation. So you get, if you can bound the right-hand side, you can get the same estimate as I already have for that matter. But what I'm after is bounds on the velocity gradient. And the tricky parts here is the PUX term, which I split up into two pieces. One using the gas law. So one is T squared and the other is rho times rho squared UX squared. And again, I have up here nu times rho. Since it's linear, I get rho squared here as well. So I can use this diffusive term to control this term here, in which case I control the pressure term. And then from this term up here, you can get good estimates on the velocity. And again, noting that rho is bounded away from 0 on a subset, you can also get estimates on velocity. Next, and all the way up here is basically the same as Navier-Stokes. You can do most of this, I think. No, you can't do this because you don't have, here you would only get ux, so you couldn't do this trick with Navier-Stokes. Right, next comes the one of the biggest differences with this system. So now I can test the continuity equation with minus 1 over rho squared, which gives me an equation for the specific volume, that is 1 over rho. And again, it's always the convective term here that is the tricky one that needs to be controlled, which is this one. And I can split it up. I have an estimate on the velocity, and to control this term, I can use the diffusive term here. So now I get a quite remarkable estimate here. I get that the specific volume is in H1, which basically means that rho is greater than 0 almost everywhere. So this is a huge difference from the Navier-Stokes equations, where there is no such result. So now I know that all solutions have to be positive. And I can use that to improve estimates on the temperature and get better time estimates on the temperature. Again, all of this is just tricks using the previous estimates. And I go back to the continuity equation again. So now I will need better estimates on rho. So I try to test the continuity equation by multiplying with rho, the standard energy estimate. And again, the convective term is the difficult part. I can split it up like so. And the last term here, that's the kinetic energy, which I have a bound for. And this term here can be controlled by the diffusive term immediately. So now I get estimates. I get rho in L2 and inf and so on, and L2H1. And now that I have these estimates, I can make better estimates. So I can go back to the continuity equation and now multiply it by rho squared. And using the previous estimates, I can improve the estimates further. But still, this wouldn't be enough to prove a weak solution. I need even better estimates. So I go back to the continuity equation and now test it with rho cubed and use the previous estimates and lift myself up further.
Can you please explain the notation? Is L2 infinity, what is that space?
The first one here.
Yeah,
that's
yeah.
L inf in time, L2 in space.
Okay. Mm-hmm.
So it's immediately what you get from here. You integrate in time this term here. So I was, when I did this, I was optimistic that maybe I could continue this process up to rho, to any exponent here, but it turns out it's not possible. You can get it a little bit better than this, but basically it will stop. And it depends on how good estimates you have on velocity, which you need in all these estimates. And those are only that good, so it stops. Okay, now back to temperature. So the problem here is that it's easy to change the equation or add technical assumptions to get better estimates. So this term here was added to get good estimates on temperature. The problem is that once you have added this, now you need a very, very good estimate in order to prove that this converges at the end of the day. So what do we need? Well, we have this term sitting in the energy equation, and we can recast it as a Laplacian. And now, to make a weak form of this, we could then, in principle, move both these derivatives over to the test function, and you end up with the t to the power 4 term. In order to get weak convergence now, we need t4 to be a little bit better than in L1. So, and that I don't have. So then I use a trick from a paper by Feiteisel, where he derives the internal energy equation for another modified system, and he used this rescaling that he multiplies the equation with. And I tried the same trick basically. So I multiply with this peculiar function here, and this gives me a new renormalized energy equation, which looks like this. So it's renormalized internal energy equation. And now using all the previous estimates. So for instance, this term here you may recognize as the one appearing in the kinetic energy, which I already have an estimate for, and so on. And this I've also handled. It was in the kinetic energy equation. So it's possible to use all the previous estimates in order to deduce that T is in L4 plus 1/12. So this sorts us out for that term when we come to convergence. And then you need to use all these estimates to demonstrate that all the terms appearing in the equation are basically in spaces better than L1. And for that, we need P in L2 plus a little bit and so on. And we also need that all the fluxes with respect to the velocity are in at least L1. So for instance, rho U is easy to show that you get a good estimate. And the trickiest one is rho U cubed that appears in the energy equation. And with the estimates at hand, I could just make it a little bit better than L1. Okay, so now next step is to see if these are at all enough, these estimates. And so I just make a formal calculation here and say that I assume that I have some sequence of approximate solutions that satisfy these estimates. Then I use the Aubin-Lyon's lemma in order to get strong convergence and almost everywhere convergence of rho U. And once I have that, you can then play some games and deduce that also U and T must converge almost everywhere. So then I move on and see what form of weak solution we can get. And so the weak form of the continuity equation would look something like this. You simply move the derivatives onto the test function, and the rho terms here are not that difficult, but the fluxes here, of course, are. But I have an estimate of this in L2 and also pointwise convergence. So you can deduce that everything is converging nicely, and also for this term. So this continuity equation is quite simple, of course. The tricky part is the energy equation. But with these estimates, like for instance this one here, knowing that it's embedded in L1, you can make all the equations work out. So it's fairly tricky, and although I have very strong estimates from strong a priori estimates, it's just enough to make it work. And for the entropy, I settled with just showing that the global inequality is satisfied. I think this can be improved. I think you can probably show that the energy inequality is satisfied locally in some distributional sense. But what I can conclude from all this is that it should be possible to get some approximation scheme that could converge to weak entropy solution. And the next problem is to find an approximation scheme that does this. So what I've opted for a finite volume scheme because I think that's the only option that could possibly work. I remained in the Cartesian frame, but the theory here can be generalized to Voronoi meshes, that is a sort of triangular meshes. And the requirements is that I must be able to replicate all the a priori estimates, which is difficult in a semi-discrete setting. But since it's a scheme, there will be error terms. So it's additional difficulties in showing that all of those goes to zero. So what I've chosen to use is a node-centered finite volume scheme. Since it has the summation by parts property, which is what I need in order to make all these sort of integration by parts mimicking stuff that I did. And the most complex estimates to derive, that's the entropy estimate and that renormalized energy. So in order to make my life easy, I looked at entropy conservative fluxes as a starting point, because then I get basically one of them for free, and I need just to worry about the other one. And there are many such fluxes derived. Then I add artificial diffusion in order to control all the error terms that I have, and I impose the boundary condition on V strongly. That means that I simply overwrite with V equals 0 on the boundary points. And the gradients here, I impose them weakly, which means that I basically set them in the flux. I set the fluxes to be 0. So this is very similar to what you would do in finite elements. And the semi-discrete finite volume scheme, it's standard. So V is the measure of the volume. This is the surface area. And you have differences in the fluxes in the X, Y, and Z directions. So this is standard. So the only problem here is to choose these fluxes such that you get all the estimates. To do that, I need some notations. I need the straight arithmetic average. I need a log mean. These always appear in these entropy conservative fluxes. And I also need 2 different averages of the velocity squared. And this is, of course, you have to do the same thing in the Y and Z direction. And I split up the flux in a convective part and a diffusive part. And as I said, I looked to entropy conservative fluxes, and the most appealing one I found to be the Chandrasekhar's entropy conserving flux. So I use that as my base scheme. It's not exactly his flux, but it's the flux is based on that one. So I modified it. And therefore, I also use his notation, this beta, which is basically 1 of the temperature. And the flux looks like this. So we have some strange approximation of the pressure, and the convective flux for the continuity equation is simply the straight average. So here it differs from Chandrasekhar's flux. And then this guy here appears in all the other fluxes in the same way. And so basically, this is the only difference from Chandrasekhar, where he does use another approximation here. So this means that this convective flux is not entropy conservative, but it works out. And then we come to the diffusive flux. So I have this coefficient that I want to be mu over rho, and here I need to choose this rho to be the log mean. And for this term, I need to choose it to be the arithmetic average. Then I need an artificial diffusion coefficient that I will basically add to the other diffusion coefficient, and it's chosen like this. So if you ignore this term, this last term here, and you set this to 1/2, then this would be just an upwind scheme in the velocity. And basically, I choose it to be 1/2 or this log difference here. And if I take it that you're familiar with standard entropy schemes for the Euler equations, where the artificial diffusion is typically scaled by both the velocity and the speed of sound. And you can note here that there is no speed of sound here. So this is much less diffusive than standard entropy schemes. And then I use this combined diffusion coefficient directly in the diffusive fluxes. So here you have just a difference in rho, which is standard. Here we have a difference in the momentum. So this is also straightforward. The energy equation, however, is rather complicated in order to get these properties. And we have a new approximation of the pressure gradients. All right, and then I derived all the a priori estimates for the scheme, which is an algebraic nightmare, and I won't show it, but you can derive everything in the same way. And here I also comment the difference with Chandrasekhar's flux, entropy conservative flux, where he doesn't use the arithmetic mean of rho u, but this instead. Formally, this scheme is first order accurate. It's less diffusive than rho, but I've also written in the paper that you can relax it to second order. And I've tried this, I've coded this and tried this, and it works very, very well. It's very robust. I've not made it crash once. So the existence is you extend all the point values to piecewise constant function, and you use standard ODE theory in order to show that you can solve this scheme for any on any grid up to a certain time. And then again, you use Aubin-Lyon's lemma to get strong convergence in rho, and you can then move on in the same way as I argued for the equation itself for B and T. And also here you can see that you can get almost everywhere convergence of the differences of the variables, which is necessary in order to demonstrate that all the error terms disappear. So I use the summation by parts property to move differences onto the test function, which takes me to the weak form. And then all I need to do is to show that all the numerical fluxes converge to the correct limits. So I've written here one example. So this is a flux that would appear in the momentum equations as it stands in the scheme. I want to see that this guy converges here. So I have to rewrite this to the flux that is actually in the equation. And this gives me then an error term. So this term here, I can argue that it converted, or this term. This term I can argue in the same way as for the equations, but now I also have the error term here. But I have some estimates on differences, so I can show that this term goes to 0. And then you have to repeat this for all the flux terms in the equations to see that this holds. So a few remarks on the existence results as such. So high order beyond 2 seems very difficult. I can't see any possibility to actually get a high order scheme that could be convergent. And the reason for that is that you need so many estimates, and you need, I've mentioned summation by parts, but you also need these Leibniz rules that you can take differences of products and get something sensible out of it. And those do not generalize in high order as far as I know. On the other hand, you can go from the Cartesian that I proved it for to Voronoi meshes without any problems whatsoever. It's the same proof. I'm also working with a student on far field and inflow-outflow type boundary conditions, and I think that can be done as well. So in this proof, I only had walls. I have another PhD student that is looking into weak strong uniqueness, and that seems to be doable at least for like isentropic versions of the equations, but we hope to generalize it as well. And what I also want to remark here is that there are many properties that a scheme must have. You see many papers and talks in conferences where people try to derive entropy or structure preserving schemes in some sense, and then they have some pet properties that they want to preserve. It is rather delicate to get convergence, and preserving some properties is not likely to be enough. And the other thing that is the key to the entire proof is the positivity, that I can demonstrate that rho and t remains positive. I also show some plots on some validation cases. So this is work I did before this existence proof with a guy in Prague. And we ran a DG scheme. And here you see 3 different plots actually. So the alpha equals 1 is the one I presented here. I initially had some doubts, or I wasn't sure how to scale the diffusion coefficient. So the alpha 4/3 is too much diffusion. And in this plot, the alpha 4/3 is not entirely, those are these lines here that do not lie on top on the other 2. But the Navier-Stokes and the alpha equals 1, which is the one I advocate now, are exactly on top of each other. So this is a shock vortex interaction. And here, here it is a NACA 0012, and it's the same story. The alpha equals 1, and the Navier-Stokes are exactly on top of each other. So this is Mach 0.5 and Reynolds number 5000. And this is the pressure coefficient. Again, these two are on top of each other, exactly the same. If you compute the drag coefficient in this case, you will see that a number of significant digits coincide between these two models. And here is another, it's the same NACA 0012, just a different Mach number, lower Mach number and lower Reynolds number. So we ran a number of different cases here. And it's the same story. It's they are on top of each other. And the same with the pressure coefficient. So the alpha equals 1 and Navier-Stokes are identical. And again, quite a few significant digits are the same for drag and lift and so on. And here is a high Mach number, 2.0. And again, it's the same story. The Mach isolines are the same. And the pressure coefficient, same story. They are the same. So I mean, you can test more, but we've tested low Reynolds number, high Reynolds numbers, or fairly high as you can get, and low and high Mach numbers. Actually, it is the low Reynolds numbers that should be more interesting, because then diffusion is more prominent. And again, also in this case, you see that you get a match of drag, lift, and moment. And we also ran an unsteady case, Mach 0.5 and Reynolds number 10,000. Again, you see that lift and drag and so on is the same to many significant digits. And there are other groups as well that have validated this model. So we have a group in Saudi Arabia. They ran similar cases as I've just shown, only for a cylinder. And so they tested a wide range of Mach numbers and Reynolds numbers, and they drew the same conclusion that the two models are on top of each other. And I also ran with a student. We looked at shock structures, and there you can also see that they are of the same level of accuracy. None is very good for shocks if you actually look into the structure. And we also looked at sound wave propagation. There you see some discrepancy, but it's fairly unclear what the experimental data is actually telling you. There is also a group in Poland that I noticed ran my model, and they were interested in the incompressible limit. And they noted that first they noted that my system gave the same results as the incompressible equations, but they also noted that it was much faster. And this is also an interesting thing. In all these simulations, my system is running much, much faster than the Navier-Stokes equations. And as of now, I have coded up the scheme I showed you, and I've been running this for Taylor Green. I've been running it for a cylinder case and an implosion in a box. And the second order, even the second order scheme with a second order diffusion coefficient is very, very robust. It can run shocks and whatnot without any problems. And if you're interested in the derivation of the model, it's published in Physica A 2018. So some conclusions. The two models, or the Eulerian model, at least in all cases I've been looking at, is as accurate as the Navier-Stokes, but it is convergent and the scheme works very well. It's less diffusive than standard finite volume schemes for Navier-Stokes equations. And I also say that there's no tweaking, tuning, or any dirty tricks. The scheme is exactly what I coded, and it works as it should. Thank you for your attention. I'm happy to take any questions.
Thank you, Magnus, for this interesting talk. So yeah, is there any questions or comments? So maybe I can just begin, Magnus. So I'm not familiar with this. So if you take classical Navier-Stokes Fourier model and this model, what you are proposing. So in terms of mathematical difficulties, for your model, you can always get bound for rho, especially the it's a bounded eye from 0. So which is to say that if you put diffusion, then that's easy to derive. So does that mean that you can also prove the convergence of numerical scheme for the classical Navier-Stokes Fourier equation if you assume that your discrete solution is bounded away from 0, just the way you did here?
Yeah, if you make that assumption, I think it's much easier. Yes.
But without that assumption, is there any result with full generality?
And as far as I know, there is no proof with any generality for the Navier-Stokes equations. But as you said, if you assume that density is bounded away from 0, you get much further with the Navier-Stokes equations. But I don't think you get all the way anyway, so I did this trick where I repeatedly where I bootstrapped the continuity equation. And that I could do because I had diffusion in the continuity equation. That gave me sort of high estimates of, or good LP estimates of diffusion. So I think you need to assume more. I think in order to get anywhere with the Navier-Stokes, you basically need to know that both temperature and density is bounded in a very high LP space. And you need to assume that rho is bounded away from 0. And none of those things can be proven as far as I know. And I don't see any way to do it.
Okay, thank you. Yeah, so any other questions or comments?
I have one. So for your model, let's say, do you have uniqueness, let's say in dimension 2?
Well, uniqueness. So this is something I'm working on with the students. So there is this concept called weak strong uniqueness, which means that, if you know that. So as long as the solution is reasonably smooth, then it's unique. And this concept, so I have a student who claims to have derived it for the isentropic version of the equation, and I think that's correct. And then we will try to see if we can extend it to the full system.
Okay. But can you expect like uniqueness in dimension 2, like incompressible case? Because you have like a additional diffusion in the density component.
Yes, in the incompressible case, I don't think you can get it. So you no, and if so, it would be quite remarkable. No, like, so it only works for the compressible case where you have varying density and you have density diffusion.
Yeah, because what I was trying to see is that, okay, in the classical, compared to the classical compressible Navier-Stokes, how it can be better. So for instance, so let's say, can you expect, let's say, global existence for strong solutions?
For
your model. For your model, maybe in dimension 2.
I mean, I don't. Global existence of strong solutions. I don't see how that can be done. But on the other hand, I'm sure that a good mathematician could get further. I'm using just the sledgehammer. But I have to say that there are some reasons why I may think that it's not possible. So I'm not sure that these equations actually will always allow a strong solution. A turbulence is still something. Well, I have my doubts.
Okay.
And I would actually argue that it's quite enough if you have a weak solution and know that that is unique. That would be good enough, I think.
Mhm. Okay, thank you.
So in the weak strong uniqueness that you mentioned, what is the regularity assumption on the strong solution that will guarantee weak strong uniqueness?
What is the
regularity on the strong solution that gives weak strong uniqueness?
Oh, I don't know that off the top of my head, but I mean, you do. I don't. You probably need a pointwise bound on the derivatives of the principal variables. That's my guess, but it's something like that.
So in extending the convergence proof to higher order schemes, will the proof become relatively easier if you assume that the solution is smooth?
Well, no, I wouldn't say so. I mean, if you can't assume that a numerical solution is smooth. I mean, a numerical solution is just a set of point values or coefficients or however you choose to represent it.
Right.
But
I'm assuming that the exact solution is smooth.
Yeah. No, I don't think so either. I mean, you still need convergence. No, it's the problem. Okay, so the problem is if you have a linear equation, then it is like that basically. Then we know that the solution is smooth, or we may assume it, and we demonstrate convergence towards it. But then basically you just need an L2 estimates, and then you're done. But here you still need all these estimates in order to know that your fluxes are converging at all. I mean, it's perfect. So this is actually the problem. If you have the Navier-Stokes equations, we may assume that, and in some cases it's true that there is a smooth solution. It doesn't help you. Your scheme could produce whatever anyway. I mean, there is no guarantee that your scheme will convert just because the underlying solution is smooth. And I think this is something that I didn't mention it, but one reason that I began to think about this is that I actually have seen this happen many times. That you can have like world-leading groups in CFD running their codes, and all of them will be able to reproduce all the known cases where they know the exact solution, or they presumably know it. And then if you give them another case, their codes may produce completely different solutions, and it's impossible to tell which one is correct. And this is the main problem that I see in this field, that people tend to think that that you somehow can know or recognize that this should be a sensible solution, but you can get quite different answers. I've seen this many times now, and I think this is just because we don't have any convergent schemes, and we can make them converge if we know what to converge to, but we don't in general.
Thank you.
Okay, so any other questions or comments?
So if we have external forces like say gravity, is that possible to incorporate in the model? And for example, can this model reproduce something like a hydrostatic solution in an atmosphere?
I'm pretty sure it can. Yeah, I haven't looked into it, but I don't see any problem whatsoever to add a forcing like gravity. I don't think that is a problem at all. But Actually, that is an interesting case. So that's actually an argument in favor of this model. So if you take a steady profile, or you look at a hydrostatic case in the atmosphere, and you solve that for the Euler equations, you don't get the same answer if you take the Navier-Stokes equations, although everything is static. Then you get a different profile of the density. And my model would actually reproduce exactly the Euler profile. So I think that's actually an argument in favor of my model.
Okay, thank you.
Okay, so any other questions?
If there's anything else that you wonder, you can always drop me an email.
Yeah, sure.
I'm happy to discuss this.
Yeah. So, I have one stupid question, but I'll ask. Let's finish this colloquium talk, then I'll ask you. Okay, so if there are no more questions, let's thank Magnus again for this wonderful talk.
Thank you.
So thank you all.